Today, I really want to provide kind of a perspective on the work that was cited in the award citation for this Frontier of Science Award, which I'm very grateful to receive. Of course, the work itself is on the screen. It's with my collaborators, former collaborators, Zhangwen Ha and Liang Fu, and published in 2016, I believe. And yeah, it was really a pleasure collaborating with them and a very fortunate opportunity to do so, and resulted in, I think, both the coining of this word fracton, which is stuck, and maybe the origin of that name may become clear later in the talk. And also, I think the work itself probably also launched maybe a flurry of additional effort to understand new kinds of quantum, sort of topological-like quantum orders in higher dimensions. So I'll really be providing a perspective on this paper and some of the work in broad terms that has happened since this paper, along with one very recent question that I think I've encountered, which I find very interesting, and I'd be very happy to chat with any of you about after the talk. So just to begin with some very broad context, so we know that quantum many-body entanglement allows certain phases of quantum matter to avoid conventional classical ordering at zero temperature. It's maybe obvious from the nature of entanglement, right, which doesn't really like classical ordering anyway. And of course, there's nice examples of phases of quantum matter that have been known for decades at this point, like the fractional quantum Hall effect, where many-body entanglement plays an essential role in evading the classical ordering that would otherwise be encountered at zero temperature, right? But we also know that, so these phases of matter have been, in the past, a term coined by Xiaogang Wen in 2012, been referred to as being topologically ordered, having topological quantum order. And these are, broadly speaking, gapped quantum many-body phases that host ground states with a degeneracy that is sensitive to spatial topology. So the topology of the manifold that I actually put the system on. Of course, that may not be so easily observable in experiment, but it has consequences that go beyond ground state degeneracy. The ground states themselves are locally indistinguishable, and they're also gapped excitations with very unconventional properties, unconventional from the standpoint of conventional quantum many-body physics. These are excitations that can have anyon statistics in two spatial dimensions. They can also carry fractional quantum numbers, as is often the case in, well, I guess in the fractional quantum Hall effect, it provides a nice example of this. And other quantum spin liquids are also ones in which the anyon excitations or other point-like excitations can really carry fractional quantum numbers with respect to a global symmetry. And a mathematical framework that's been very successful at describing this is topological quantum field theory, which really, in mathematical terms, does an assignment of some equivalence class of curves to ground state sectors on a manifold, right? That assignment is done in some very special way, but that assignment alone encodes all of these properties that I've listed on the screen: ground state degeneracy, gapped excitations, and also implicitly the local indistinguishability of the different ground state sectors. Now, with this backdrop of topological quantum order in 2012, I think it's also important to understand what was going on, and I think is still going on in quantum error correction, right? So the locally indistinguishable nature of the ground states in topological quantum orders provides an ideal Hilbert space in which to encode quantum information. And we know that the theory of quantum error correction is built on the following idea: you can't clone an unknown quantum state. So unlike classical error correction, where redundancy really helps classical codes to succeed, in quantum error correction, the problem is really that we want to protect a single instance of an unknown quantum state, of an unknown qubit. And that sounds very, very hard. But entanglement is what sort of rescues us, in particular, this kind of quantum many-body entanglement. And if I have a locally indistinguishable basis of quantum many-body states, then of course superpositions of these states cannot easily decohere, right? Especially if I assume that the environment that's doing the decohering only interacts locally with my system of interest. At least it'll take some very long time before that decoherence happens. So a key question for quantum information that was true about a decade ago, and I think is even true now, is when is a quantum memory self-correcting? So what do I mean by self-correcting? I mean, I have some quantum information that I want to protect. I encode it in the quantum error correcting code. You can imagine that this code is a ground space of a topological quantum order, right? And then something happens, and that something is a coupling to an external bath, which is thermal at some temperature, right, at temperature T. And I've drawn it as this caricature where I have lightning bolts hitting my quantum error correcting code. And the question is whether some kind of recovery of this quantum information is still possible, even in the presence of interactions with an external environment that's threatening to thermalize my quantum system, right? Another way that people in quantum error correction really think about this is, which is useful to know going forward, is that a quantum error correcting code may be coupled to an external bath for some time, and then for a fixed size of the quantum error correcting code of the number of physical qubits, there may be a time that I couple it to a bath, after a sufficiently long time, it may be the case that recovery is not possible. And I'll refer to that time, that critical time above which recovery of the initial quantum information isn't possible, as the lifetime of the encoded qubit. Now, the question to ask is, how does this lifetime scale as I take the thermodynamic limit of the quantum error correcting code? And a self-correcting quantum memory is one in which that lifetime scales exponentially, grows exponentially in the system size, okay? And if that isn't possible, then self-correction is not possible, okay? So what does that mean? It means that as I add more and more degrees of freedom to my system, I'm improving my ability to recover from the spurious errors that are being encountered when I couple to an external environment, instead of that entropy contributing to the decoherence of the quantum states that I want to protect, right? Which it could also have happened. This is intimately related, but not exactly the same as the thermal stability of zero temperature topological quantum orders. Okay. Now, with this background, I think it was actually known, and sort of an interesting statement, that stabilizer quantum error correcting codes with string-like operators. And when you think of string-like operators in a topological quantum order, you should think of Wilson lines or dual operators that create at their ends, fluxes or something. That these stabilizer quantum error correcting codes with string-like operators cannot function as a self-correcting memory in low spatial dimensions. So that's not included on the slide, but it's in low spatial dimensions 2 and 1. I believe this paper showed it to be the case in 2 dimensions and 1 dimension. And we also know it to be true sort of colloquially in 3 dimensions, but this was sort of a rigorous argument. So with this, these two perspectives, we have topological quantum order as an interesting way in which quantum many-body systems can order at zero temperature. We also have a potential use for them in quantum error correction, but there we also potentially want to find a self-correcting quantum memory where quantum information is naturally protected from the effects of thermalization. So a natural question emerges, are there stabilizer quantum error correcting codes that lack string logical operators, that lack string-like operators that create gapped excitations, if you want to think about it as a topological quantum order, above the topologically degenerate ground states? Now, if you think of conventional lattice gauge theories, ZN gauge theory, or even your favorite topological quantum orders in 2 dimensions, described, say, by Levin-Wen, kind of string net type models, you know that all of them have string-like operators. They all have point-like charges and are therefore really sort of forbidden from acting as self-correcting memories. So this question seems to evade a very simple answer, right? Now, in this context, a very interesting paper came out in 2011, which is from Jungwon Ha, saying that a stabilizer quantum error correcting code exists in 3 spatial dimensions that lacks string logical operators, and therefore is potentially a candidate for being a self-correcting quantum memory. It is also an example of a kind of quantum order that is probably like topological quantum order. The code space for the quantum error correcting code is formed of many body states that are locally indistinguishable in the same way that topological quantum orders are, right? So I've just drawn for you what cause code, the code that he proposed in 2011, looks like, just to show you that it's not a very simple one to look at. So the code space of this quantum error correcting code can be identified with the ground space of the Hamiltonian that's shown on the screen. It's a Hamiltonian on a cubic lattice with 2 qubits per lattice site. And the individual interaction terms in the Hamiltonian are shown. Z refers to the Pauli Z operator and X refers to the Pauli X operator. The notation is such that ZZ or ZI really refers to Z tensor Z or Z tensor I on the 2 qubits that are at every lattice site of the qubit lattice, right? So this looks like some monstrous Hamiltonian, and how it was actually found originally is its own story. But this is interestingly what's known as a frustration-free stabilizer Hamiltonian. And what that means is that all interaction terms in the Hamiltonian commute with each other. They commute with the Hamiltonian. Furthermore, they can all be satisfied individually and independently. And what that means is that the ground states of this Hamiltonian can really be constructed as the set of states which actually minimize each interaction term separately, right? And that is the statement that this is a frustration-free Hamiltonian. Frustration hopefully being a familiar concept even in classical systems where, say, antiferromagnetic interactions on a non-bipartite lattice are frustrated, right? There's not a zero energy configuration of interactions, of those sorts of interactions. But here, this is frustration-free. So at least in theory, we know what the ground state is. It's the simultaneous eigenstate of all of the operators that show up in the Hamiltonian with minimal eigenvalue, right? Okay. Now, what are the properties of this code space, of this quantum error correcting code? I told you it has no string operators. What does that really mean? Well, first of all, the code space is very odd. So I remember I told you that in a topological quantum order, the topological degeneracy is, obviously, as the name implies, only dependent on the spatial topology of the manifold that I put this sort of error correcting code or this topological quantum order on. But the degeneracy of Haas code has this very funny property. So I take an L by L by L cubic lattice with periodic boundary conditions, and let me parametrize L as a power of 2 and offset by an integer in the following 3 ways. And let me then take the thermodynamic limit, keeping this parameterization fixed. So doing so, you can find a very erratic behavior of the ground state degeneracy. If the system size is off by 1 from a power of 2 to the n plus 1, then the ground state degeneracy is always 2, regardless of what L is, on the L by L by L cubic lattice with periodic boundary conditions. It's 4, 2 to the 2. But the degeneracy, which is D, actually grows subextensively in system size if the system size is exactly a power of 2, right? So you add just one more row of lattice sites in the x, y, and z directions, and all of a sudden the ground state degeneracy grows like 2 to the 4L minus 2, right? So in fact, the degeneracy is some very complicated number theoretic function, which was actually not known in the original paper by Ha, but was found more recently. But it has this property. So it's clearly not a topological quantum order at least in the sense that I defined it. So all of the states in the code space are locally indistinguishable as with topological quantum orders, and more precisely, the reduced density matrix on a topologically trivial subsystem in any state that lives within the code space is exactly the same, okay? And in that way, this would function as a good quantum error correcting code. The ground state is also gapped. And like I said, because it's a frustration-free stabilizer Hamiltonian, the excitations above the ground state are associated with the individual interaction terms which are violated in the Hamiltonian, right? What that means basically is that there are terms which in an excited state, there are interaction terms which may not take on their minimal expectation values. And I'll say that these sort of terms are associated with the excitations. They're like localized clumps of energy density above the ground state. And you can ask what the properties of these excitations are. These excitations actually are very fascinating because they're immobile. They're immobile in the sense that if any local operator attempts to push these excitations in any direction, doing so will necessarily incur an energy cost. So it's not actually possible to move them through any local operation. In fact, the condition is even more stringent. So the energy cost for separating an excitation by some distance r grows logarithmically in that distance, okay? Which is very bizarre. It should be thought of as being extremely bizarre because this is a translationally invariant model, right? It has a translation group. It's not that I've localized some gapped excitations by imposing upon the system some external potential which would localize these excitations and force there to be some complicated energy landscape. It's really some property of quantum many-body entanglement in this ground space and in the low-lying excited states that contributes to this growth in energy cost. Okay. And these conditions, along with some results that were recent at the time by Bravi et al., allowed one to show that Haas code actually defines not just an error-correcting code, but a gapped phase of quantum matter. That is, it's stable to all local perturbations, at least all of the properties that I mentioned, up to some finite strength. Okay. Great. So just to visualize Haas code, assuming that this is potentially the first time that some people in the audience have maybe thought about this or have seen this, and certainly I don't think in the literature this is maybe so clearly illustrated. So in Haas code, like I said, the interactions are associated with cubes on the cubic lattice, right? Again, excitations are associated with violated interaction terms. And so naturally, the excitations are associated with the dual cubic lattice, right? They're associated with sites of the dual cubic lattice, where violated interaction terms are naturally sit, right? So, to visualize this phenomenon, you can imagine that you start off with a configuration of 4 excitations in Haas code. So this is not a ground state. You start off with a configuration of 4 excitations in Haas code as shown on the screen. So the red dots are just some adjacent sites on the dual cubic lattice. And the corresponding interaction terms there have been violated with respect to their ground state expectation values. Okay, and I just want to illustrate the sort of minimally expensive way that you can separate these excitations away from each other, because I told you that you have to pay an energy cost that grows logarithmically in separating these excitations. Right? What does that process even look like? Well, the minimally invasive way to do this is I'll just sort of illustrate it now. You can act locally near one of the excitations to transform it into 3 other ones. So of course, if each excitation costs some constant energy, then I've gone into some higher energy state, right? I can perform the same game again. I can apply some local operator, and I can convert the 2 excitations that were sitting relatively close by to each other into 2 other excitations that are now living along, say, the x-axis and the z-axis. So as I'm performing these operations, I'm drawing more and more sites and more lines on the dual cubic lattice. Just for clarity, I haven't shown the whole thing. Still, you can see that I have some complicated mess of excitations, not maybe terribly complicated, but I'm in some higher energy manifold relative to the initial state I started off in, which only had 4 gapped excitations, right? One final move will actually fix the problem, and that final move can be applied to the top 3 gapped excitations on the screen. And this is the simplest thing that a local operator could do. It can annihilate them and annihilate them into just a single excitation of Haas code. So what we started off with was a series of 4 gapped excitations that were separated from each other by, say, 1 lattice site on the dual lattice. And we've ended up with another excited state, which costs the same amount of energy. But now these excitations are separated by 2 lattice sites, right? But of course, in the intermediate steps, I had to go through intermediate excited states where more energy had to be paid. It turns out that the number of moves that you have to actually perform in order to separate out these excitations by some distance grows exponentially in the distance that they're being separated. And that's the minimal number of moves that one has to apply. And it's actually not too hard to argue by some inductive arguments that the sort of minimum energy barrier that one has to overcome in that process must grow logarithmically in the separation of these excitations. One thing that I forgot to mention on the previous slide is that that's not really the full story. The excitations that I drew could be separated by, say, 2 lattice sites, but they can't be separated in this manner by an arbitrary number of lattice sites. That number of lattice sites actually has to be a power of 2. So they cannot be separated by, say, 3 lattice sites in the x, y, and z directions. That's a state that's actually in a kind of different superselection sector. Okay. So maybe this gives you some flavor of the kinds of moves that local operators are able to do. I haven't told you what those operators even are, to manipulate and move the excitations that are available to us in Haas code. So the question, after this paper really was, how generic is this phenomenon? Are there other examples of non-topological quantum order beyond Haas code? Something that I want to emphasize, which I think wasn't really known at that time, and I think is not so appreciated even now, is that there were already classical codes in which very similar phenomenology to Haas code was already known to exist. Okay, and what I mean by that is will be apparent in just a second. So let's just consider the ground space of the following Hamiltonian, which is really a classical Hamiltonian defined on the triangular lattice. And it just has 1 qubit per lattice site. And this was considered more than a decade before Haas' paper by Newman and Moore. The Hamiltonian is very simple. You take qubits on the triangular lattice. You take some upward-facing triangles on the triangular lattice. And you define an interaction term, which is a ferromagnetic interaction between the 3 spins. It's just Z1, Z2, Z3, where Z is the Pauli Z operator, right? It's a classical Hamiltonian. There's no sigma X term or anything. Newman and Moore, computer scientists, had their own motivation for thinking about this classical error-correcting code. But this very simple-looking model, it doesn't look like it has any symmetries, right? It doesn't have a global Ising symmetry or anything. But it actually does have some very sort of almost perverse symmetries that are very sensitive to the system size. Okay. In fact, the ground space degeneracy on an L by L torus, so the x and y directions are shown here, and if I impose periodic boundary conditions with respect to those x and y directions on an L by L torus, you actually find that the ground state degeneracy has this very weird property, which should remind you of Haas code. If L is a power of 2, the ground state is non-degenerate. But if L is off from a power of 2 by 1, the ground state degeneracy grows exponentially in L. Okay. So this should be puzzling. It's not at all obvious looking at this Hamiltonian that it has that structure, okay? Especially because of its brutal simplicity, right? There are excitations also above these degenerate ground states, even above the non-degenerate ground state, that are associated, again, with violated interaction terms. Of course, trivially, all the interaction terms commute in this classical system. And those excitations are also point-like, and they're associated. These point-like excitations have the same property as in Haas code. They can only be separated by some distance r, which has to be a power of 2, by incurring an energy penalty which is of order log r. Okay? This is also in 2 dimensions, not in 3. But I want to emphasize a very sort of interesting point, which is that these properties are due to an exotic fractal symmetry which arises in this model, which is very sensitive to the boundary conditions. Only shows up when the system size is 1 off from a power of 2. And also, unlike Haas code, these properties are extremely fine-tuned, right? This symmetry that I've identified, this fractal symmetry, which I haven't drawn for you, is easily broken by local symmetry breaking terms, right? I can perturb this Hamiltonian with other terms, keeping the Hamiltonian classical even, and I will immediately lift this degeneracy to something constant or even non-degenerate, right? So that's very, very different from Haas code, and that's the difference really between a classical and a quantum error-correcting code, right? A classical code is one in which local indistinguishability of the code space is not a requirement, right? But that is in a quantum error-correcting code. Okay, so this lacks the one key property that makes Haas code topologically quantum ordered, right, in some sense. So to add to this list of questions, what is the relation, if any, to classical fractal codes? And the kind of answer to this, I think, was really sort of provided in our paper, at least the start of the answer to this question. And I think that kind of developed, led to a lot of interesting subsequent developments. So basically, the summary is the following. There are gap phases of zero temperature quantum matter, gap states of zero temperature quantum systems in 3 spatial dimensions and also higher, with gapped point-like excitations with restricted mobility, like the immobile excitations of Haas code, and a ground state degeneracy that grows exponentially in the linear dimension of the system. So broadly speaking, this equation should be taken with a grain of salt. If I put the system on a 3 torus with linear dimension L, the ground state degeneracy will grow with an envelope that increases exponentially in L. Okay, it doesn't have to be a monotonic function of L, but it'll grow with that envelope. And that's consistent also with the behavior in Haas code. And furthermore, these phases are stable to all local perturbations, and they can be understood as the deconfined phase of a certain lattice gauge theory, which is obtained by developing a prescription for gauging subsystem symmetries. So subsystem symmetries are symmetries that are intermediate in some sense between global symmetries and gauge symmetries, which are strictly local. They are symmetries that live along lower dimensional manifolds or lower dimensional subsystems, the size of which tends to infinity in the thermodynamic limit, but nevertheless it's not extensive, right? So planes, lines, even fractal objects can be subsystems, and on which we can define subsystem symmetries. And referred to these as Fracton phases of quantum matter for reasons that may become clear in just a moment. But really embedded in this is the answer to the final question that I wrote in the previous slide, which is that really these classical codes like the Neumann-Moore model are in some sense in higher dimensions dual to Fracton orders. There's a duality that relates those classical Erk-Fracton codes into quantum ones that have true topological order, which is non-perturbable, in some sense stable to all local perturbations. Okay, so equivalently, there's instead of thinking about this as gauging, I can think about really that there's a duality between quantum systems that have subsystem symmetries and phases of those quantum systems that spontaneously break those subsystem symmetries, or phases in which those symmetries are restored. Those phases and phase transitions are dual to a kind of confinement transition in a very exotic lattice gauge theory. And that confinement transition describes the phase transition between what I'll call a Fracton order, a deconfined phase in which you have gapped excitations with restricted mobility properties or which are fundamentally immobile, and a confined phase which is really trivial, right? So, so that duality machinery is kind of implied by this gauging relation. And finally, just because I think of the number of mathematicians I think were around at this conference, I'll mention that the algebraic techniques that were used to study these frustration-free stabilizer Hamiltonians led to, I think, a lot of progress and kind of a very interesting understanding of how generic the Fracton phenomenon is, at least at the level of solvable lattice models. Within this framework, it was actually possible to show, and this is a statement that can be made very precise, that Fracton orders can sort of be generic within exactly solvable models, and that's a space that can actually be parametrized in some sense, with some restrictions for frustration-free stabilizer Hamiltonians. Okay, so let me just illustrate this correspondence, this duality prescription that leads to this relationship between classical fractal codes or classical codes with subsystem symmetries and Fracton models. So there's a duality that I think everyone in condensed matter is familiar with. It's a duality that's not defined in the sense of IR dualities that we think about in quantum field theory, where there's a duality that emerges really in a low energy description of a system that's not really true at the UV level. These are UV dualities that I'm going to talk about that can be written on the lattice. So we can think of a dual description of the quantum Ising phase transition in 2 dimensions. So I have a 2-dimensional lattice of spins. I have a global Ising symmetry, and I have an order-disorder transition with respect to that Ising symmetry, which is captured by the Hamiltonian that's shown on the screen. So this phase transition we know is in the classical 3-dimensional Ising universality class. But just for the sake of exercise, we can try to think of a dual description of this Ising phase transition. What does a dual description mean? It just means that the defects that are being proliferated starting from the ordered state to get to the disordered state, I can phrase the entire transition in the Hilbert space that is formed of those defects, right? In this case, those defects are the Ising domain walls. The domain walls, when they proliferate, when the line tension of the domain walls goes to 0, in essence, then one has the disordered phase of the Ising model, right? Now, one can define dual Ising spins that live on bonds of this square lattice and measure the presence or absence of a domain wall. But there's a very important point here in this duality, which is that now we're thinking about extended objects. And in order to faithfully reproduce the Hilbert space of the domain walls, I have to sort of abandon the tensor product structure that I'm familiar with in the ordinary Hilbert space that we think about in condensed matter, right? The reason for that is because domain walls never end, right? Domain walls form closed loops. So it's not sufficient for me to specify the state of the a domain wall configuration by independently specifying these dual Ising spins at every lattice site. I have to make sure that they satisfy some constraints so that I'm faithfully reproducing domain wall configurations in the original system, right? And that's really what makes the dual description of the transverse field Ising model a gauge theory, right? The confinement transition in a gauge theory, and it's a gauge theory which you can think of as having no dynamical matter. There's a Gauss's law that emerges, and that Gauss's law is just characterizing the fact that domain walls don't end at all, right? So one of the species of excitations is absent, and the Z2 flux is still there, right, and this Gauss's law you should think of as being analogous to Gauss's law in electromagnetism, where here the Z2 there's some Z2 analog of it that's telling you that strings can only end on Z2 charged objects, which are absent in this theory. Right. But this duality can actually be used to establish a number of key properties which are very powerful in the context of Fracton orders, which I'll review. First of all, one thing that maybe isn't so obvious with the duality at a first glance, but is obvious when you think about it a little bit more, is that the disordered phase on the left-hand side is what's dual to the deconfined phase of the Z2 gauge theory on the right. Basically, the domain walls have to proliferate. It's only when they proliferate that we obtain this gauge theory description. So really, in some sense, it's the excitations above the disordered phase that are related to the Z2 flux in the deconfined phase of the gauge theory. Right? This is a UV kind of duality. So every state on the left-hand side has some corresponding state on the right-hand side that we can think about. This state correspondence also gives rise to an operator correspondence on both sides of the duality. And one consequence of this operator correspondence is the following. Operators that break the Ising symmetry on the left-hand side, on the transverse field Ising side, map in the dual description onto non-local operators, regardless of whether they were initially local or not. Okay, that's very important because we know that the symmetry is very important for defining the disordered order transition and even those disordered phases in the transverse field Ising model. Of course, I can add a symmetry breaking field and completely destroy the transition. But that symmetry breaking field maps onto some highly non-local operator, which is not natural to add in the gauge theory, right? Okay. So in that sense, we've converted an order which is sensitive to symmetry, which can be easily destroyed, into a kind of disorder that is really insensitive to local perturbations, right? Up to some finite strength. And the final property here also is that the Z2 flux on the right-hand side in the Z2 gauge theory, its mobility properties and other properties that it has, say it's braiding with the Z2 charge, are related to the mobile gapped quasiparticle excitations above the disordered phase of the Ising model. Okay. One last point, which I think is non-trivial, and it's an interesting one to remember, but formed a key part of our paper, is that it turns out that the degeneracy on the symmetry broken side of the Ising model actually provides a lower bound to the symmetry to the degeneracy on the deconfined side of the gauge theory on the right-hand side, even though those two phases are not dual to each other. That actually, that's true on any manifold. Of course, it's trivially true here. You have a degeneracy of 2 and 4 on the torus, respectively. That actually provides a hint on as to the kinds of classical models that one might want to consider that when dualized would give you some kind of topological quantum order, you might say. One in which you have an extensive degeneracy, but the ground space is still protected against all local perturbations. So, the next natural step was to sort of bootstrap that intuition and to consider quantum systems with intersecting subsystem symmetries, not just global symmetries. The reason for this was that, these are systems where when these symmetries along lower dimensional manifolds are spontaneously broken, the ground state degeneracy is naturally extensive. It scales with system size because there are so many symmetries to be broken, right? A simple example, which actually was also considered, the classical version of this model was considered by Wegner in the 70s for very different reasons. We refer to this plaquette Ising model. It's a lattice model in 3 dimensions with a qubit per lattice site that has planar Ising symmetries along x, y, yz, and xz planes. So these are intersecting planes. One can consider a Hamiltonian that describes phases in which these planar symmetries are either all spontaneously broken or restored. Okay, and what one finds is that in the dual description of that model, you obtain a deconfined phase of a generalized gauge theory in which the gauge flux can only be created from the vacuum in clusters of 4. It can only be created from the vacuum in clusters of 4, like I said, for the simple reason that the disordered phase of this model is one in which the excited states, which are symmetric with respect to the subsystem symmetries, are ones in which spins can only be flipped in clusters of 4. That is a requirement that follows from the subsystem symmetries very trivially. But the duality converts that statement, that very simple statement, into an order which is actually stable to all local perturbations, right? So this is a Fracton order, and I'll explain why it is in just a moment, for it's very simple. But it's one that's very different from Haas code. Well, from the vacuum, I said in this deconfined phase of this gauge theory, I can create gapped excitations in these clusters of 4 that are shown on the screen. E is maybe this kind of Z2 charge or flux that you can associate and that you can think of as being these individual gapped excitations. This is kind of the elementary move that allows me to create one of these clusters of 4 excitations from the vacuum. And now I decide to attempt to move a single one of these charged objects using an arbitrary local operator with this constraint that I can only create or annihilate them in these clusters of 4, right? And then I run into the same problem as in Haas code. I try to move this excitation, but in doing so, I create 3 more. And in that sense, the individual excitations that appear here in this cluster of 4 are immobile, and attempting to move them will necessarily move one into a manifold of excited states that cost even more energy, right? But there's a key difference from Haas code, which is that if a pair of these excitations live close together, then a local operator can actually move them, but it can move them only along a line that's orthogonal to the line that joins them. So there's really a mobility hierarchy of the quasiparticles in this problem. There are individual excitations that are completely mobile. There are pairs of them that are mobile along lines. But the only truly mobile excitation in the theory is one in which is the topologically trivial one that can be created with a local operator. Okay. So this Plaquette-Ising model in a transverse field allows one to do a kind of use this machinery of duality to obtain what we refer to as the X-cubed Fracton order. So this is a Fracton model in which the excitations have a Fracton-like character. There are these quote-unquote line-ons, which are objects, gapped excitations that are only free to move along lines, and this is all while preserving some kind of translation symmetry on the cubic lattice. There are also excitations that are conjugate to the ones that I mentioned, which turn out to not be fractons. They're mobile along lines, similar to the line-ons that I showed on the previous screen. Okay. Interestingly, the degeneracy of this model is actually exactly the following. On the 3 torus, so with length Lx, Ly, Lz in the XYZ directions, the degeneracy grows exponentially in the following way. There's a funny sort of -3 factor, so the degeneracy is 2 to the, on the torus with, length L in all 3 directions, it's 2 to the 6L -3. And I'll explain, the sort of machinery that allowed us to make that statement in just a moment. Interestingly, of course, if you ungauge Haas code, then you also get some sort of classical fractal liquid, classical error-correcting code. And this looks like a very natural generalization of the model that Newman and Moore wrote down in 2 dimensions in higher dimensions, right? Okay. Now, I want to mention, and I think this is a part that's been sort of not so well appreciated, I guess, but so we know that a TQFT assigns to a ground state an isotopy class of closed curves, right, on a manifold. And in contrast, the ground states in Fracton orders are associated with curves according to a very fine equivalence relation, which yields an extensive protected degeneracy. An algebraic description of these curves was really essential to establish the properties of Fracton orders and to prove properties like the indistinguishability of the ground states and to establish the immobility of the excitations. So this algebraic framework, really based in commutative algebra, was kind of laid out by a paper by Ha in 2013. And I think that machinery was really used to a very great extent. It was applied to fermionic quantum codes in a separate paper that we wrote, and then also applied to these dualities and Fracton orders in the paper that was cited. And that was really the core machinery that allowed us to make all of these statements precise and indeed rigorous. Because ground state indistinguishability is a very hard thing to show in conjunction with a lot of the other properties that are demanded of topological quantum orders and of these fractionalized excitations. So an example which I'll illustrate here is that certain excitations, like in the X-cube model, live on sites of a dual cubic lattice, and the locations of these violated interaction terms can actually be specified by a Laurent polynomial over a finite field. it's the field, the choice of the field is actually determined by the sort of Z2 nature of the excitations in the problem. And it's actually because it's a qubit model. And it's the rule for mapping a sequence of excitations into a Laurent polynomial is actually very simple. One just takes the locations of the excitations and one writes down a polynomial, which is a sum of monomials that tell you the locations of where the excitations live when translated from a reference point using the elementary lattice translation vectors. So here's a configuration of 4 excitations that could show up in the x cube model, and I would translate this as 1 plus x plus y plus xy in this algebraic formalism. So thus the space of all excitations can be associated with a Laurent polynomial ring over this finite field. And it's a Laurent polynomial ring because I can translate forwards or backwards in infinite space using the lattice translation vectors on the cubic lattice. So the super selection sectors, which really are of interest to study the ground state degeneracy in these Fracton orders, belong to a quotient space where one is taking this Laurent polynomial ring and quotienting out by the set of excitations which can be created by local operators from the vacuum. The idea is that you have the space of all excitations that one can write down, and if you want to think of the equivalence class of all possible excitations under local moves, that equivalence class is in one-to-one correspondence with the ground state degeneracy. That's true for ordinary topological quantum orders. It's also true for all of these Fracton models and any topological quantum order that one can think about. But formally, this quantity I that I've written down can actually be thought of as what's known as an ideal that's generated by finitely many elements in these stabilizer quantum error correcting codes. What that really means is that the excitations in, say, Haas code or in the X cube model are created using a finite set of elementary moves acting on the vacuum. And those elementary moves can be specified by a collection of polynomials like the one that I had on the previous screen. And in addition, I can require that the cubic lattice has some periodic boundary conditions by incorporating into this ideal that constraint that when you translate by L lattice sites in one direction, say, you come back to the same site. So, the dimension of this quotient space, which one has to study to determine the ground state degeneracy, it actually turns out that that's very simple to get some intuition for. Because quotienting out by an ideal or quotienting out by any set essentially amounts to setting, identifying the elements of that set to be equal to 0, right? And in this case, quotienting out by an ideal amounts to setting the generating elements of the ideal to actually be equal to 0, and that specifies what's known as an algebraic variety. So one has these polynomial equations. The polynomials themselves describe the elementary moves that create the excitations from the vacuum. And setting them equal to 0 defines for me a curve. And the dimension of this curve, really the dimension of this variety and its scaling with system size is what determines the scaling of the ground state degeneracy in these Fracton orders. It's actually very simple to get intuition for when a model might have the property that is desirable for Haas code, where it has an exponentially growing degeneracy, even though it may be very hard to prove when exactly that happens. Okay. So, let me conclude by, just sort of saying that, there's a sort of incomplete landscape of Fracton phases that's come about in the years since that paper. So there's gapped Fracton orders, which loosely divide into models that are like the X cube model or non-abelian generalizations, and models like Haas code. And then there's other more recently discovered examples that actually fit outside of this framework, infinite component Chern-Simons theory, which was sort of discovered by Xie Chen and collaborators very recently. They're gapless examples of these orders, which are kind of fall into their own class. And they're also kind of a zoo of Fracton-like phases where point or string-like excitations exist with a sort of reduced mobility. I'll wrap up by just saying that I think one of the most important and sort of interesting questions that's come up for me here, which I unfortunately have run out of time to actually describe, is that there are really some remarkable new symmetries in quantum many-body systems that we're still, I think, grappling with trying to understand what their continuum description is. And in particular, I think that there are actually gapless systems that have some very exotic symmetries that are similar to the symmetries of, say, Haas code. which we nevertheless don't actually have a good way of writing down in the continuum, but we can understand in very specific lattice models. So I'm happy to answer questions about that after the talk, since it's over now. But to sort of shamelessly advertise that I think that's an ongoing topic of study over the past few years, which I think is very fascinating, but probably needs a lot of creative input. So thank you.
So questions? Question will be technical. So about the spatial framework, which uses the CLF2 because of the D2 prefix. And for the conventional comparator order, if we use the Z4 or Z2, so it's quite different. Z2 is only historical, and for Z4 we have a feature structure.
Yeah.
So I'm talking about the Fracton case, because for the Z4, it's no longer a field. So maybe some empirical statement is no longer true. So does this give you extra consumption compared to the standard Fracton?
Yeah, that's a great question. I think that is very possible. In fact, most of the studies that we've performed are restricted to FP, where P is prime, right? So it's a field, I think if one thinks of that, there are Fracton models that people have written down, which are like ZN generalizations of models that can be written down for the Z2 case. But I think a lot of the machinery that works very nicely in the case where we're working with a polynomial ring over a field actually doesn't work so well in the case where you have, say, Z4 elements. Yeah. 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 Yeah, so this is the part I didn't get to. But yeah, so this model actually has a very funny symmetry. This is a sort of rotor model, which is a generalization of this model by Newman and Moore that I talked about earlier. You have a rotor degree of freedom on each side of the triangular lattice, and on downward-facing triangles, you have this interaction term. This model has two global U1 symmetries, which are very simple. You can label the sites on the triangular lattice as A, B, or C sublattice sites. And then the A and B sublattice sites, you can shift theta by a constant, which is either positive on A and it's positive on A and negative on B. So you can do that everywhere, and that's a global symmetry. So this model has two global U1 symmetries, but it actually has a very exotic fractal symmetry also. And that fractal symmetry is actually the following. If I take the system to have be L by L with periodic boundary conditions, and I take L to be one off from a prime power, so P is prime and K is just some integer, then there is actually a staggered rotation of the phase. The staggered rotation of the phase over a triangular region. This is a triangle with side length, which is a prime power. And this is actually an exact symmetry of this problem, of this model. Now, I won't explain, since I have even less time, what the intuition is for this symmetry. You can see, though, that it's an exact symmetry of this problem, let me just say, but only when L is one off from a prime power. Yes. Yeah, right. Yeah, so here one can actually do a duality, and it turns out that the dual system is very, this model is very close to being self-dual. So in low dimensions, right, we can do, say, Kramers-Vanier duality, and you obtain more or less the same description that you started off with. You don't obtain a gauge theory, right? So that's actually what happens in this problem. You obtain a dual description, which is not a gauge theory, which is not what you would expect for like the XY model in 2D, right? But the interesting thing I think about this model, though, which I think invites further studies in higher dimensions, is that even for a generic system size, forgetting the subsystem symmetries and all this stuff, let's say I just have a thermodynamically large system. If I do this kind of staggered rotation over a finite region, and that region is large, though, it's prime power P to the K, then I will be in an excited state, but that excited state will actually cost an energy that goes to zero, like 1 over P squared. So I can do this symmetry transformation over a large region, and as that region becomes larger and larger, I've essentially produced an arbitrarily low energy state to the ground state. Right? But the transformation is not close to the identity, right? It's not like like a Goldstone mode or something where I'm doing a rotation of the phase by an infinitesimal amount on all sides. This is actually a dramatic rotation, but it produces for you a state that's actually gapless. Right? So that's, I think, something that we don't really understand. We actually know in this model that if you turn on quantum fluctuations, that it's actually unstable. So there is a large U phase in this model that's written on the screen, right, which is just a mod insulator. And there's only one phase when you turn on U. And there's only one phase for a reason that only the Goldstone modes associated with breaking the global U1 symmetries are enough to destabilize the phenomenology that I discussed just a moment ago. But in higher dimensions, that may not be true. So I think it's sort of interesting to maybe study these sorts of problems in 3 dimensions. Yeah.
I would like to ask you to satisfy the depth and for the question is, for example, the Fracton physics that is Fracton goes like this problem system shown. Please specify what's the subtle things.
What's the difficulty? What? Yeah, well, okay. There are certain gapless Fracton models where you can really understand them as a kind of generalized electromagnetism, and the idea is very, very simple. I think this was written down by Pretko in 2017, 2018, and the idea is that normally in electromagnetism, you have just a Gauss's law, and on a closed manifold, that also, if I write down a U1 gauge theory, I can have no net charge, right? When I integrate that over the closed manifold. You can also imagine that I have a constraint that's not just saying that I have no net charge, but I can also demand that there's no net dipole moment. And there's a corresponding local kind of generalization of Gauss's law that I can write down that requires that that's the case. So with those 2 constraints, you find that the charges in the theory behave like fractons. So yes, with restricted mobility. The funny thing about those theories, though, is that if you Higgs them, then you don't actually get Fracton models that are like the ones that I've shown. So if you Higgs them by condensing some of the charges, you end up with actually more or less conventional Z gauge theory. And so those field theories and those models are a priori sort of very different from the ones that are being shown here. So those have some continuum field theoretic descriptions. And there have been lots of attempts, I think, to come up with continuum field theories for the Fracton models that are gapped that I discussed as well. With fractal symmetries, I mean, there are some models like the one that's shown on the screen where people have written them down, have identified some kinds of fractal symmetries. I don't know how it's possible to think of that in the continuum, those symmetries, just because there's not really a long wavelength description of that symmetry action, right? It's not close to the identity or anything.
We can discuss. So let's thank Sagar again, and let's come back in 6 minutes.